Today on the Numenta on Intelligence podcast.
So you see someone who believes the Earth is flat, and you give them all these facts that don't fit that model.
Yeah.
So the Earth is flat predicts certain things.
Yeah.
Right? And they will do their damnedest to try to fit
their model.
There's new facts into their model.
Yeah. Right.
No matter how, that's what they're going to, otherwise you have to throw the whole thing away and start over again, which is a very disconcerting thing for them.
It is. It's uncomfortable to
sure.
have to throw away a whole frame of reference.
I mean, basically, the models you build of the world are your reality.
It's your belief system.
It's your belief system.
Yeah.
It's your reality. This is what, that's what it boils down to. There is no other reality in terms of your head. This is it.
Yeah.
And so if you say, well, you know what, everything you believe, it's these references, and you have to start over again, then it's kind of like, oh, you're going back to square one.
Jeff Hawkins on defining intelligence. What is it? What makes us intelligent? How is our intelligence different from a mouse's? We're narrowing down the answers to some pretty existential questions. I'm Numenta Community Manager Matt Taylor, and thanks for listening to Numenta on Intelligence. All right, so I'm here with Jeff, and we're going to talk about intelligence in general and about how we might define it.
Yeah.
And so I like to think about this from the question of evolution, in a way like, what do our brains do for us now? What did they evolve over time to do for us as humans or as just life forms, animals?
Yeah.
It's a good place to start.
That's a good place to start. Well, sure, evolution is a good place to start for almost anything related to living. Biology. I mean, I kind of feel it that way too. I start off by saying, I tell an evolutionary story, right? And the evolutionary story says, well, life formed on Earth, billions of years ago, and was pretty dumb for a long time.
Yeah.
It was bacteria basically for the first billion or so years, and then when things started to move, movement requires. There's two ways you can move. You can move blindly, which is pretty stupid. No point in moving if you don't really, But if you're going to move with a purpose to achieve something, you have to have some sort of knowledge about the world, and that knowledge could be encoded in genes, the genetic material. But it's some sort of knowledge. Even a bacterium has a motor plan, which is, if I can move, I'll turn towards gradients. That's my strategy. That's my model of the world. But any animals that start moving around a lot, then they need to have some sort of concept of where they are and where things are. And so all of a sudden, if you're going to have mobility, then you're going to have some sort of way of learning the structure of your environment and knowing where you've been and how to get back to some place. If you're going to go home and you're going to go away from it and you got to come back, you have to have some way of doing that.
Right.
And so nature evolved a series of ways of sort of building maps of your environment, and different animals do this different ways.
Right.
And mammals have a certain way, and that was first evolved in this hippocampal complex, the grid cells and the place cells, which is really a map of the world and learning where you've been and knowing what you did this morning, things like that. And then finally, the theory that I propose here is that released around Numenta is that that sort of mechanism that was highly evolved in the hippocampal complex, grid cells and place cells and things. That method of mapping your environment became the evolution discovered they could make a sort of a generic version of that and make lots of copies of it. And this is what we think the neocortex is. This is the whole thousand brain theory of intelligence.
So you're saying the mechanism that the hippocampal entorhinal complex has done for an organism to navigate through its own environment is copied thousands of times.
Well, it's been refined and copied, so it's not a direct copy.
So but it's running in parallel. A bunch of them running.
So
in parallel.
Our theory that came out in the paper in December on the framework paper,
right,
and a couple of papers before then, basically is arguing that there are grid cell-like cells throughout the neocortex, and that the same mechanisms that were basically used to figure out where you are, typically a rat is in some environment, where we are in some environment. We have a sense of where we are. That's in the grid cells in your entorhinal cortex. That same mechanism was sort of nature saying, hey, I can make a sort of a slimmed down generic copy of this mechanism, which is a mapping mechanism.
Yeah.
It's basically learning maps of the world, if you can think of it that way.
Right.
And now it's copied throughout the neocortex. So now so intelligence is taking that sort of mechanism which was evolved for specifically one thing: navigation and remembering where you've been.
Egocentric navigation.
Well,
right?
yeah, I don't want to use those terms, but it's navigating in some rooms. I have to learn like where's my environment, whether it's a woods or my house or the rats nest under your house or whatever it is.
Right.
Learning that where things are and how to get around and navigating. Whether it's, and so it's complex. That system is very complex to do this, right? There's egocentric and allocentric models there in the entorhinal cortex. So but again, that's been under evolutionary pressure for a very long period of time. Of course, in the neocortex, which we think of as this sort of the organ of intelligence, is fairly new. It hasn't been around very long at all, and it got big really rapidly.
Yeah.
And so the idea that it got big really rapidly by taking a single thing and making many copies of it, and that single thing we believe is sort of an essence of what you see in the old brain, the hippocampal complex, the entorhinal cortex. And so now we are. So this is a very long answer to your question, but instead of building just maps of rooms and where you are in the forest and things like that, we now build maps for objects. And instead of moving just my body moving through the world, it's my finger moving relative to objects or my eyes moving relative to objects. And so now we have started having the ability to build models of other things besides environments. So in the bottom line of all this is that intelligence is tied to the quality of the model that you build about the world.
Right. Yeah.
And to say we're smart, and we say, oh, we're smart because maybe we know about the planets, we know about black holes. That just means we have a model in our head for those things.
Right.
And
the meat of that is in the new part of the neocortex. And it's interesting that the neocortex spread so quickly evolutionarily. That means that it was doing something that was really useful for the survival.
The only way you can get something big like that is quickly in evolutionary terms is just make more copies of it.
Yeah.
Right.
Which is essentially what it is.
Yes, it is. So that was Vernon Mountcastle's big proposal in the 1970s was that the neocortex got big rapidly. But you look at the structure is very similar everywhere. So he says it's the same algorithm being operated on 100,000 times. We have 100,000 or 200,000 copies of the same circuit.
But each one they're working together to provide a rich model of reality.
This is the Thousand Brains theory, which of course is in the December paper.
Yeah.
Is the Thousand Brains theory of intelligence says you got all these parallel models. They're basically doing. There's tweaks on it, but they're basically doing the same thing. But what they can model different things. They're not all these models are different. They're not like it's not redundant.
Right.
They're parallel. And so there are thousands of models that are modeling the visual space, and there are thousands of models of modeling the auditory space, and there's thousands of models that are being used in language and so on. But each column is essentially modeling its inputs, doing a sensory motor modeling of its inputs. It doesn't know each column doesn't know what it's doing.
Right.
But depending on what its inputs are and what motor behaviors it can control, that's what it builds a model of.
Right.
And some of them are going to be building models of input from your eyes and your fingers. Some are going to be building models of models that they're getting input from other parts of the neocortex.
Right. Right.
So, but they're all doing basically the same thing, and then they vote. Again, this is all in these papers we've written. They vote by because often they're observing the same object.
Yes.
Or they're thinking about the same thing, and so even though they're slightly different, each part of my somatosensory cortex represents a different part of my fingers, my skin. And when I touch this cup, they're all measuring a different part of the cup, but they're all sensing the cup, and so they can vote and say, yeah, I only have this limited input, I have this limited input, I have this limited input, but let's vote together. And together we can agree that this is, we all know about cups, but let's agree that, we all can only agree on right now that this has to be this cup. It can't be anything else.
So how can we take what we know about how that works and help it to define what intelligence is then?
Yeah. So I think this is one of the, I think today we're in this sort of a weird state about intelligence, especially machine intelligence, which is dominated by the idea that intelligence is a capability. Can I do something? Can I play Go better than the best human player? Can I drive a car better than a human? Or can I whatever, pick your favorite task, analyze a medical scan and check cancer.
Yeah.
And so this is how we met today. This is how the world of AI measures their progress.
The value of the application.
Well, just against human level behavior.
Right.
Take a task that a human does.
Right.
Say, can I get a machine to do that task? And this goes back to Turing with the Turing test, right? He proposed this, the imitation game, which we now call the Turing test.
Right.
But which is all about matching human level performance.
Right.
But I don't think that's a really poor way of measuring intelligence. Yeah. There's lots of intelligence things out there today, animals, who couldn't possibly pass the Turing test. They can't speak to us,
They're vastly more intelligent than what
Yeah.
we've created.
A dog is pretty intelligent, right? And some dogs more than others. And so, the Turing test doesn't capture that at all.
Right.
Or a human who speaks, Portuguese is asked to take do a Turing test with someone who speaks English. It's meaningless. It's like, they can't do anything.
Yeah. It's like we're framing intelligence in the wrong way.
Yeah, we're framing the wrong thing. So we're using this sort of ends method to do it. Like, well, if you can do X.
Right.
The problem with when you do it that way is that you can always engineer a solution to do X better than anything, right?
Yeah.
So we end up.
That's what we have today.
Yeah,
That's
we do.
AI
We have these.
situation.
We have basically these AI systems that are really good at one thing, but they can't do anything else.
Yeah.
Nothing else. And then you can argue, well, I could take this convolutional neural network and I can train it to play Go, and then a moment later I can train it to play, Pac-Man. Well, okay, fine. Then a moment later I can train it to drive a car.
Yeah, but does it understand anything that it's doing?
Well, yeah. So here's the real question to go back. There's a couple of things. First of all, you ask, what kind of model of the world does it have?
Right.
Right.
Or does it have a model?
Yeah. Well, anything that acts has a model. It can be a very poor model. I mean, a model basically says
It could be a hard-coded model.
It could be a hard-coded model. The point is, if you have some input and you're going to act on it, then you need a model to decide how to act. It
Right.
could be a really stupid
Be
model.
a lookup table.
It could be, but it's here's instructions on how to do this.
Right.
Or it could be learned. But the point is, in our brains, we have this a fairly general purpose way of learning models of the world.
Right.
My brain can learn mathematics. It can learn Portuguese if I so desire to do so. It can learn to play guitar. You've been playing guitar recently. We can learn all kinds of things. I can learn art. I can learn engineering.
Anything.
We can, well, anything we know of, but not anything. But pretty much all the things we think about of human endeavors across all time are done using the same basic algorithm. And not only that, we do them all simultaneously. It's like I'm not dedicated to one thing. So I have this. You've got a picture in your head right now. You've got this model of the world. I know you're interested in that, astronomy, and we're interested in space and physics and time and space, and then you also have a model of your family and your car and how to fix the things in your house and all these things. So we have this very, very rich model that we've learned, and a single organ, the neocortex, can learn this very, very rich model of the world.
Yes.
And then if we want to ask how intelligent something is, we really need to ask, what is its model like? And how rich is it? And by what methods does it work? Because some models of the world are very, very specific. And some ways let's say this way, some way things learn can be very, very specific.
Yeah.
If I set up a Go playing, or just say chess. If I set up a chess playing computer, I want to build the world's best chess playing computer. The model may be built around chess. It may be like, there's the only movements this thing can make are chessboard movements, and the only thing you can know are chessboard positions. Mm-hmm. And so we structure the information in this computer in chessboard coordinates.
Right.
And so that's a great framework for learning chess.
It's the only frame of reference the system knows.
That's right. So we talk about grid cells like a reference frame.
Right.
But it's a very general purpose reference frame. I can apply grid cells to all these different things. It's more like XYZ Cartesian coordinates. It's very general purpose. You can apply XYZ coordinates to lots of different things.
So you could say grid cells are like a general purpose tool our brain has decided to use to map things in their own reference.
Well,
frame.
It's a general purpose. So we talk a lot about reference frames on here. So the reference frame is just a way of locating something and assigning knowledge to some place. So
in relation to other things.
Yeah, you need to know where things are in relationship to the other things, and that's what you need to know. Basically, that's how you assemble information to something useful, like what makes a computer is because these components that are in relation to each other and how they move relative to each other and so on.
Right.
So you need a reference frame for storing structure about anything. And there's different types of reference frames. A good general purpose reference frame is the one I just mentioned, the XYZ one.
Cartesian
coordinates. Yeah. That's pretty general purpose. You can apply it to any three-dimensional or two-dimensional or one-dimensional structure, and you can add more dimensions if you want.
Yeah.
Grid cells are another general purpose one. They're similar in that regard, but they work differently than Cartesian coordinates in a clever way. And just a little aside here, the reason they're really clever is because there is no origin to them, but the locations are tied together by movement. And so it's like a Cartesian coordinate frame in some sense, and that it's general purpose, but it's movement decides how you get between things.
Right.
So, but you can think of it as a general purpose reference frame. So I can use a general purpose reference frame to learn chess. I can say, oh, well, there's a sort of a board here, maybe I'll use my sort of XY Cartesian coordinates for that.
Sure.
And it won't be as good as a chess coordinate frame.
Right.
Because I could build a specific one, or reference frame, just for chess. Yeah. It would be probably better.
You could encode the movements of the pieces.
Yes, and so basically the only movements that exist here are the chessboard movements,
right.
and so that system could think in chess very, very well. But if I asked it to think about coffee cups or learn the structure of a coffee cup, it would totally fail.
So you're saying today's AI, our weak systems, are sort of hard coding their models to specific frames of reference.
Well, I wouldn't say that. I would say some might be. It definitely on a case by case basis.
Yeah.
If someone built, I don't know how the team that did AlphaGo did their thing. But if they encoded knowledge about chessboards into it specifically, and
or Go boards.
Go boards. Then it might be spiffy.
Well, they have to.
Well, no, actually, it turns out most of what's going on in convolutional neural networks these days, there's no actual.
Oh, it's just mimicking, or.
Well, there's no assigned reference frames. There's no even knowledge. It essentially has to be learned, but no one really understands how it's learned, and so you end up with this sort of weird sort of mapping between inputs and outputs that no one really understands very well.
Right.
So the fact that there is a mapping between inputs and outputs tells me there has to be some sort of model. Whether that model has a reference frame is hard to tell.
Right.
If all I'm doing is sort of saying, oh, here's an image and here's a label. Here's an image and here's a label. I actually don't need a reference frame. It could just be this big, complicated lookup table in some sense.
Yeah, just a wad of math.
Yeah, it's just but if the system is going to make predictions and move and make and sort of say, if I do this, what's going to happen here, and so on. Then you think a reference frame is required, but we know in brains have reference frames. And if you don't have a generic or general purpose reference frame, you cannot be smart. You cannot be generally smart.
Right. And you're talking about, so there's different types of reference frames.
Yeah.
Like I like to think there's the easy separation of I have an egocentric reference frame. I am in the center of it, and my environment is the frame of my organism exists. And then there's the reference frame of every object that I could imagine has its own reference frame. Yeah. And then I can somehow combine them, so I can imagine an object in my hand that's not there.
Yeah. Let me be clear. When you say there's different types of reference frames, there's two ways we can think about that. One is, what is the physicalness of the reference frame? Like chessboards versus Cartesian coordinates versus grid cells versus latitude and longitude.
Yeah.
Those are different types of reference frames.
True. I'm not talking about that.
Yeah. A reference name can then be applied to different things. So reference frames are always, in some sense, anchored to something.
Yes.
Right? That's what you were referring to.
That's what I was referring to.
Right. So
like in space.
Yeah, well, anchored, even if it's not in space, it's just anchored to something.
Each other.
So, like, you can anchor a reference frame to my body, and that becomes an egocentric reference frame. So you can think of it as the coordinates related to my body.
Right.
And that's what we think is going on in the where regions in the brain.
Right.
Then you can have reference frames that are anchored to physical objects, meaning if the object moves, the reference frame moves with it.
Right.
That's what we think is going on in what regions in the neocortex. Then there are, those are two big ones.
Right.
So.
Those working together allow us to model all the objects sort of in our space.
Well, I can model objects using like what reference frames, like a reference frame around an object. And
but for me to know there's a chair there and there's a table there.
For you to know where it is relative to you and how to get to it. Mm-hmm. So there's this. Excuse me. There's these well-known when people first discovered the what and where regions in the neocortex. These parallel sensory paths for vision, hearing, and touch, and they first discovered them in vision, and it was very odd because if a human has a damaged what pathway in vision, they can look out at the world and they can't recognize things. They can look at the computer or this cup and they won't say, I don't know what that is. I can't tell you, but they know something's there and they can reach for it.
they can actually grab it.
They can grab it. They're surprised when they grab it. It's sort of like, and then by the way, then they know what it is.
Because they touched it.
They touched it.
Yeah.
So they're like, oh, that was a coffee cup, of course. Well, but the point is, with only the egocentric reference frame, you can know how to reach things, and you can know where things are relatively. You cannot recognize what this thing is because you need an object-centric reference frame to do this. You flip it around, and the people who have a damaged where pathway, but a functioning what pathway, they say, oh, there's a coffee cup.
Yeah.
And you say, well, why don't you pick it up? And they say, I don't know how to do that.
They can't relate it to
they don't know where they see it. They know it's out there, but they don't know how to move their hand to that thing because they've lost this visual egocentric reference.
I don't know what's worse.
Yeah.
Awful.
So when we say we model the world, we have to be careful here. I model the coffee cup with object-centric reference frames.
Sure.
And I modeled the solar system that way, and I modeled the universe that because I can't actually go out and touch those things and move around, right? But to be a functioning animal with moving limbs, you have to have egocentric reference frames.
Yeah.
And so you take a more primitive animal. I always like to talk about like a crocodile, and they see some food. They may not have a clear image of what that food is or how to exactly its shape and its but they know how to reach it.
Yeah.
They know how to move their face toward it and bite the thing. So it's really important to be able to like move your body to capture some prey or something like that. So there's these limited abilities to do these things in other animals. So these ideas aren't just in the neocortex; they're in the old parts of the brain too.
But the interesting thing you've mentioned about the crocodile, you think about a crocodile versus a mouse and how they eat.
Yeah.
A mouse will have little bitty fingers, and it will manipulate the food really carefully.
I saw this video. They're showing this just in the last year for the first time, and I didn't realize this. Do you think a mouse paw is not very interesting? Right?
Yeah.
But they pick it up like like the Shakespearean actor looking at the skull. It's like, what's this little thing? I'm gonna eat it this way, huh? And it's like a mouse does this, and it's like really surprising.
A crocodile couldn't even.
Yeah. The mouse looks at the piece of cheese and decides which way to hold it, so they get to the right part. It's pretty impressive. They do it really quickly, so if you don't slow down the video, you miss it.
Yeah.
But they go.
But it must mean they've got a rich model.
They have a model. It's not nearly as rich as ours, of course, but the idea that they can see the structure of that object, which what that tells you is that they see the structure of the thing they're about to eat.
Yeah.
They can then they recognize its orientation and what features are on it, and then they can move their hand to grab it in the right way to bring it to their mouth in the right way to eat it. And so it's not like it's just some piece of food and they don't know what it is or what its shape is, or they're not just stuffing it in their face. They're picking at it like you and I might pick at a piece of fruit that's got some bad spots on it.
So while we're talking about different types of animals, let's talk about the intelligence spectrum, because we're more intelligent than mice, obviously, and you just probably say mice are more intelligent than crocodiles.
Well, I don't know. There's so many things that are confused here. So first of all, we can ask the mechanisms by which the animal makes a model of the world. Are those general purpose mechanisms or are they specific mechanisms?
Okay.
Then we can ask, what is the capacity of that model? Because clearly a mouse's neocortex is quite small. And it's the size of a small postage stamp at best. Well, a rat's about that big. So mouse is probably even smaller.
Yeah.
So it's not going to have a very big model of the world, but it learns that model the same way you and I learn that model. So it's a general purpose model, but very limited capacity.
Right.
Whereas an ape, it's got a much bigger model, like a monkey, and then there's humans. We have this really big neocortex. So we all learn the same way. We all use the same mechanism. We're all general purpose learners. We all learn, we learn rapidly, continuously, and using sensory motor inference, and we have the same sort of rich modeling structure.
Right.
But we clearly, so we can divide animals along or systems along that line. What is the mechanism you're using to learn? And then there's the capacity issue.
Yeah.
So often we think about intelligence as also people who know a lot of things, right? Well, that's a separate issue. That's like, okay, well, a mouse, I would say, has the same sort of mechanism for learning that we do. It's a mammal. It And so it's going to have the exact same neocortical structures are very similar, but it's just limited. Sometimes I make the analogy with computers, right? What is a computer? Well, there's a formal definition for a universal Turing machine.
Sure.
So it's a mathematical thing, whether something's a universal Turing machine or not. And you can build them out of Tinker Toys, you can build them out of silicon, and all computers that we think of today as computers are universal Turing machines. Not all. You can build an ASIC chip that does something. It's not a universal Turing machine, but computers are.
Yeah.
But computers come in all these different sizes, right?
Yeah.
You can get the teeniest little computer. It's still it has still a CPU, still has a program, and maybe only 8 bits.
Right.
Has a limited amount of memory.
Powers your toaster.
It toasts your toaster. And that's still a universal Turing machine.
Sure. Yeah.
And then you have the room size computer.
That just means you can program it to do different things.
It means it works on the same principles of general purpose computing.
Yes, general purpose.
If you gave it enough memory and enough time, it could compute anything.
Yeah. General purpose is keyword there.
Right. It's basically has this set of attributes which, in theory, could solve any problem if you gave it enough memory and enough time.
Right.
But
and there's this huge spectrum between toaster and supercomputer.
That's right. But they're all universal Turing machines.
Right.
And there are other systems that are not like that. There are other systems that solve problems. Like I could have a toaster. My toaster. It's funny because I think these new toasters are really amazing, but my older toaster wasn't so amazing. It had some mechanical things that let it figure out how to toast much.
Yeah.
And so it did sort of the same functions, but it wasn't as good. But there was no computer inside of it, right?
Mm.
So, but it did many of the same things. So anyway, so you have this one spectrum, which is the mechanisms that are being used, and in the computer world, that's universal Turing machines. And then there's a section of capacity, and then there's a third thing, which is like, okay, what has it been programmed to do? So now we have three similar metrics on intelligence. We have what are the basic mechanisms by which the model is being learned. So a mouse and a dog and a human all have the same mechanism.
And we're talking about reference frames.
Well, we have a general purpose reference frame, and we the whole mechanism that we use in building a model of the world is what we wrote in the framework paper, and so we just all use the same one.
Right.
Then there's the capacity issue. So mouse has very limited capacity. We have much more capacity because we're just bigger brains.
Yeah.
And then finally, the equivalent to what the programming is like, well, what have we learned? I could have a big human brain and not have learned very much, right? I just didn't get an education.
I don't think about that very much, that aspect of intelligence. You can have a system that is potentially intelligent but hasn't learned enough to be classified as intelligent yet.
So when we think about intelligence, we have to think along these metrics, because it's the same thing with computers. Those 3 metrics for computers: the method in which it operates, the capacity of the system, and then what it's been programmed to do. In intelligence, we have the method of learning a model, which is reference frames and general purpose and sensory motor inference and all those things, then, because they can vary there.
Yeah.
So maybe the Go computer doesn't have a general purpose reference frame.
Right.
Then there is the capacity of the system. How much memory does it have? How big a brain? How many columns do I have? How many neurons? How many synapses? Things like that. And then there is what has it been trained to do? What has it learned?
Right.
And so you and I could be two intelligent people and have very different sets of knowledge about the world. So if I was raised in the woods by wolves, and you came along, well, Jeff, what do you think about this? About the Milky Way? And I said, what the hell are you talking about? I don't know what the hell Milky Way is, right?
Right.
And so, and then
you'll talk to me about the spirit in the sky.
Yeah, whatever. Or I'll talk to you about these plants that you don't know about these plants.
Yeah.
Man,
don't eat them.
That's right. You don't know that. So we can have So then we have to be really careful. And I think the problem we have in the field of AI is that people aren't talking about it in a structured way like this.
Right.
They're not talking about these different components of intelligence.
How something is intelligent?
These 3 components: the method by which it works, is it general purpose or not? We have a general purpose learning algorithm for learning models of the world or not? Then the capacity of the system, and then what it's been trained and how it learns.
Right.
And so right now we're focused basically on, hey, can I beat some humans at something?
Right.
Which is really the wrong metric completely.
Yeah.
I think the world of AI in the future, if you go out far enough, is going to be dominated in machines that don't do things humans do at all.
Yeah.
So why try to recreate a human for all these things? Let's have them do things. Some overlap perhaps, but it's not the goal to pass a Turing test. That's the wrong goal.
Yeah. Along those lines, I want to talk. We just talked about the intelligence spectrum. I would assume that we humans are probably near the top of that intelligence spectrum on this planet.
Well, on this planet, I would say.
On this
I would say
planet.
because, yeah, there's no question about it.
So one of the things that we do that perhaps intelligences down the spectrum don't, maybe, is have this ability to have these rich, abstract models of things that don't actually physically exist in nature. How does the idea of reference frames apply in that arena?
We touched on this in the frameworks paper, and I'm writing a lot more about it right now. First of all, the way I approach this is not saying like, oh, I see that these are references. It's more like, no, the neocortex does these things.
Yeah.
And the neocortex looks the same everywhere. Therefore, these things are based on reference frames. It's like, let's figure out how.
Right.
As opposed to Sargent saying, you know what, I think language is based on reference frames. No, it's like, damn it, language must be built on reference frames, so let's think about it a bit.
Yeah.
That's such a big question, Matt. There's lots of ways you can attack it.
We could use examples, because I'm a programmer, and so I think in different ways in different engineering situations, and that feels like, for example, if I tackle a programming problem in one language, I will pull a certain reference frame into my brain to execute commands in that language. It has similarities to other languages that I've used in the past, like all these different areas of expertise.
Let me get really, really highbrow about this a bit.
Sure,
okay.
sure.
So it's kind of hard to bring it down to like everyday experiences, but knowledge. Let me just try to define what knowledge is. Knowledge is sort of information or facts arranged in a useful way.
Correct.
Okay?
Agreed.
So I can have a whole bunch of facts, and I can say, yeah, you and I see the same facts, but if I'm knowledgeable about it, I look at those facts and, oh, I know those things. And what does it mean to know those things? What I believe it means to know those things is that I take that information and I can assign it to a reference frame. Everything has a location. And that reference frame, and what you get with a reference frame is you get the ability to navigate through these facts. And you navigate through the facts is like navigating through a room. I'm moving my finger relative to a coffee cup. But in this case, I'm moving my location in this space of facts or space of things to achieve certain results. So an example I've often used as a mathematician, where you say, okay, some people look at mathematics equations and they go, oh my God, this is like Greek. I can't understand the word that's going on.
Right.
But a mathematician looks at it, and all these equations are friends. They're like, they're friends. They're like, oh yeah, I know that, and I know that, and I know that. Even numbers are friends. You know, oh yeah, 169, that's 13 cubed. Oh yeah, that's right. So, and what they do is, and so the one thing you think about is like if I'm trying to solve a mathematical theorem or something like that, I start with a set of points, a set of equations, or a set of things I know are true.
Right.
That in some reference frame, and I'm trying to get to a new point in some space. And I'm trying to figure out the right behaviors to get me there. And the behaviors are mathematical operations. So if I do a Laplace transform here, I get this. And if I do this kind of transform there, I get that. And if I do a multiply, I get this. And so in this sense, where the behaviors are mathematical transforms that move you through a space of mathematical constructs or concepts.
So, like a theoretical space? Or?
It's literally using grid cells.
Yeah.
But the space, there's two things. What are just think of it as grid cells like a map, okay? It's like an n-dimensional map. So what are you assigning to the map locations? You're assigning mathematical constructs. You can think of like equations, maybe, okay?
Yeah.
When you move, what are you moving? Well, you're not moving physically, but you're mentally moving through this space by applying certain operators. Instead of moving, instead of the operator being flex this muscle, the operator is multiplying, divide. And you get the same basic thing. You're moving through this space of ideas, and so that's what you do when you're thinking about something. So this is the general idea that high-level knowledge is the organization of concepts in a reference frame, and your ability to be really, really smart at something is knowing how to navigate and what kind of behaviors you do to get someplace. Another example would be a politician. A politician wants to get some bill enacted. They have something they want to get, and they have all these obstacles to get there.
Yeah.
Right? So they say, I'm at this point here, where this is the state of the world, and I want to get to this thing here where this thing gets passed.
Yeah.
How do I get there? And they have all these potential things they could do. They could have a rally, they could hold a forum, they could do some sort of publicity, they could get some endorsements, And the politicians experienced enough to say they know what will happen when they do these different behaviors.
Right.
And so since your choice of behaviors is your choice of which way you want to move through the space of political things.
So his model of politics as he knows it is a reference frame that he's evolved over time due to his experience in that field.
Yeah.
Right.
More likely a woman because they're smart about these things. But what becomes an expert is an expert can look at the same facts, but they have through experience they've learned what happens when you do things.
Right.
So as a programmer, you sit there and you say, okay, I want to solve some problem.
Yeah.
And you say, well, I might solve it using this kind of sorting system, or I want to use this kind of structure, or I want to use this framework, or I want to even this tool. And you, as an expert, know exactly what would happen to do those things.
Yeah.
It's very equivalent to being an expert in the woods. I go out for a walk with you, and we say, you know what? We need to find a source of water. We're getting really thirsty.
Right.
If I spend a lot of time in the woods, I'll say, yeah, I understand all this. I see, and I bet you I know there's water down there because I've learned these kind of patterns before.
Yeah.
And so I recognize this scene as
the lay of the land.
Yeah, I understand this. I
stream.
see these trees, and I see that kind of tree, and I see these hills over there, and I hear these sounds. To me, I understand this stuff. It fills in. I have a reference frame.
You may not even have to think much about it.
No, you have a reference frame. It's just like seeing when you see this coffee cup. You don't say, "Oh, where's my reference?" And you say, oh, "That's a coffee cup." Well, a person who spent a lot of time in the woods will look at that same set of data that you look at and understand it.
Right.
And they'll say, oh yeah, well I know how to do that. I know how to get to the water because water is typically going to be this kind of thing down there, right there. And you'd be going, how did you know that? Right? And same thing, if you've never been exposed to something, an everyday object like a coffee cup, if you were raised in the woods and never saw any kind of physical thing like this, you might look at it and go, I kind of see what it is, but you wouldn't immediately go, that's going to be great for carrying the fuel we need to carry, or whatever, right? So that's what makes an expert. An expert is someone who's spent enough time looking at and experimenting with various pieces of facts or data or concepts, whatever they are, that they've learned the correct reference frame or a good reference frame to assign these facts.
One that's close to reality, I would assume.
Well, yeah, reality makes it, what makes it reality is that the reference frame is accurately predicting what's going to happen.
Yeah, I guess that's more important, accurately predicting what the organism is going to happen.
You might have two different...
Even better than reality.
Different people can take the same set of facts and organize them in a different reference frame.
Absolutely, yeah.
And we see this a lot.
Yeah.
That doesn't happen for everyday objects as much, but we see it for things that are conceptual. And so we can, different religious beliefs take the same facts about the world, we all observe the same things, and they come to completely different conclusions about what would happen when they do certain things.
Right.
And that's a case where, the reference frames aren't reality.
Right.
They can't all be correct.
No,
Most, all the different beliefs we have in the world can't all be, they conflict with one another. They cannot all be correct. So one could be correct. Probably most of them are wrong, or all of them are wrong. But the point is, that's the test of reality is, or test of the accuracy of a model is how well it predicts the future. And when we don't really have good data about the future, people can get it wrong, or if they limit the amount of exposure to what they see.
Yeah.
Or
just the data being given to the intelligent system is biased in any way.
Yeah. So you see someone who believes the Earth is flat, and you give them all these facts that don't fit that model.
Yeah.
So the Earth is flat predicts certain things.
Yeah.
Right, and they will do their damnedest to try to fit
their model,
their new facts into their model.
Yeah. Right.
No matter how, that's what they're going to. Otherwise, you have to throw the whole thing away and start over again, which is a disconcerting thing for them.
It is. It's uncomfortable to
sure.
have to throw away a whole frame of reference.
I mean, basically, the models you build of the world are your reality.
It's your belief system.
It's your belief system.
Yeah.
It's your reality. This is what that's what it boils down to. There is no other reality in terms of your head. This is it.
Yeah.
And so if you say, well, you know what, everything you believed, it's these references, and you have to start over again, then it's kind of like, oh, you're going back to square one.
In a way, I mean, you think about how these are represented by neurons in your brain. A reference frame you can think of as a physical structure. I mean, it is caused by a physical structure, and if you have to tear it down and build it back up, it could be painful.
Well, you
Not
wouldn't be tearing away the neurons, but you'd have to redo all of the. It wouldn't be physically changing. You'd have to redo all the connections with synapses.
Sure, but you'd have to ignore all of the predictions that you're getting that are telling you it's flat. It's flat,
just
right?
be like starting over.
Yeah. But it's hard because
imagine
you have to drop your beliefs, and that's the hard part, is dropping what you think you know.
Well, I mean, nature has designed us to want to build models of the world.
Yeah.
That's what we do. That's what the first number of years in our life are.
We feel rewarded for it, right?
Yeah,
when you realize something works a certain way, you're like, you feel good.
And that nature, there's a evolutionary survival advantage to that, right?
Absolutely.
So like we can learn new models of the world. Each new child that's born gets to learn anew, and there's an advantage to that. That means we can adapt very rapidly. We can adapt during our lifetime.
Yeah.
But if you once you've built your world model, and you've been living your life around it, then someone comes along and says that entire thing is wrong, or some portion of it's wrong.
Yeah.
That's very upsetting. That would be all of a sudden you feel vulnerable. It's like I have a model that makes me successful in the world, and
in a way, it's part of you.
Yeah, that's right. And so now it's like feeling lost. You know, if you're out in the woods and all of a sudden you can't anchor yourself in the woods. Every tree looks the same, and now your reference frame is lost. You literally, if you cannot locate yourself in the reference frame, you feel lost.
Absolutely. Yeah.
That's not a good feeling. That's an emotional thing.
Physically or emotionally.
Yeah, and that's how people feel what they're trying to, people who don't like math, they look at these math grades, they feel lost. Or if I was trying to understand someone speaking Russian, I would be lost.
Yeah.
I would feel like, oh my God, I can't do anything.
Yeah.
So that's an uncomfortable feeling. And so
you're always grasping for anchors, like this looks somewhat similar, this looks similar.
Yeah, that's right. So we have these reference frames, we have all these models of the world, we want to stick new data into our models of the world.
Right.
And by if you have to abandon one of your basic models of how the reality is, then you feel lost, and that's an uncomfortable feeling, and you don't know what to do, and you don't know how to act, and it's just like being lost in the woods.
So that's great. Let's sum up with those three things that you mentioned before that we're saying define intelligence. The reference frames.
Well, I say the method by which the system learns.
The method.
Yeah, which is going to be intelligent, you have to have a general purpose reference frame.
Right.
So grid cells are a general purpose reference frame. There are other reference frames that are not so general purpose, like latitude and longitude, or more specific, or chessboards and things like that. So you have to have a general purpose reference frame. You have to, of course, build a model of the world around using that method. So there's a lot of things involved in that: sensory motor movement and continuous learning and so on. But
by building a model using the general purpose reference frame, you were saying we're going to have a general purpose model.
It's like saying that's square one.
Yes.
Right. To be truly intelligent, you have to at least have the mechanisms. It's like the universal Turing machine.
The tool.
You have to have the basic substrate, which can learn different things through movement.
Yes.
Okay? And the next thing is the capacity of the system. That's a simple one. Yeah. You can learn more and build bigger models.
That's what a lot of the work is happening today, and AI is still in capacity.
Yeah, yes.
Memory. How big can we? How deep can we go?
but if we're talking about intelligent systems, then of course you say, why is a dog smarter than a mouse, and why am I smarter than a dog? It's mostly to do with the capacity of the system.
Yeah.
Not completely, but mostly. And then finally is, what has the system actually been trained on?
Right.
Again, you could take the world's largest supercomputer and have it play tic-tac-toe.
It won't be very smart.
Well, that's fine, but I can't take the world's largest weather simulation and run it on the computer in my toaster, because I can't do it in any kind of real time that'd be useful.
Right.
So those are sort of the three metrics, and we just confuse them all the time.
Yeah.
And I think it's even worse than that. We confuse them because we only most AI looks at what humans do.
Right.
And only what humans do. And then, even then, like passing the Turing test brings us into a whole other domain, which is like, well, now you're trying to emulate the emotional capabilities of a human. And my definition of intelligence we just talked about does not include emotions. It doesn't mean human-like.
Right.
It doesn't mean, it's more Spock-like than did I get that right? I never.
Yeah, it's Spock.
I never watched those.
He's a Vulcan.
So I think he was like smart without emotions, something like that.
Yeah.
Yeah. Okay.
Yeah.
So think of Spock, and there was maybe you want to build a machine that mimics a human and shows emotions, but that's, to me, is not intelligence. That's a separate problem. It's a separate issue.
That's something that could be additional to
it's like that's a flavor. You can tack on
interoception or whatever you want to do with your robots.
If you want something to be a caretaker robot, maybe you want that thing to have some emotional states and
or be empathetic in some way.
Right. But I don't think that's intelligence. That's that's part of the human experience.
Yes.
But if you think about the neocortex itself, the emotional centers are not in the neocortex. They're in the old parts of the brain.
They contribute to all of our models of things.
Yeah,
in
they contribute
ways.
to how we learn. It's a longer topic, but
sure. We'll do another talk about that.
Yeah. But basically, you think of it like we have this super sort of Spock-like thing on our heads, the neocortex.
Yeah.
It sits on top of a very emotional older system.
Yeah.
They interact, but you can think about the 3 quarters of our brain that's just the neocortex. That's really, even though it's influenced by what we learn, it's influenced by emotions and so on, it is actually an emotionless model.
Sure, it's driven by its input.
Yeah, it's basically, what is the structure of the world? And
Right.
can I discover that structure of the world, whether it's physical objects and
Right.
or mathematics or politics, whatever. I'm going to try to learn the structure of the world in an actionable form so that I can now see new things, place them in this model, know how to act related to them and so on. But those are the 3 basic things, and we just don't have that conversation enough in AI. AI is
Right.
dominated by how well did I do on this particular task, and if I was trying to do an image classifier AI system, all that matters is you got the best performance. That's it.
Yeah.
It doesn't matter how you did it. It's important, but that doesn't. You get credit for being the best.
Right.
And so people are just we're not sort of moving in the direction of saying, well, how general purpose is it? And what else can it learn? And how did it learn it? And all those things. And so we're not asking these questions. No one's sitting around saying, well, people do point out that the chess playing computer doesn't seem to know anything else.
Yeah.
But they don't have the why. Why doesn't it know anything else? It's because it's got a chess reference frame, and that's all it's ever been trained on, and it probably can't learn anything else. Anyway, it's not a simple one binary answer. Those 3 things all have their separate dimensions.
Yeah.
But I think the computer analogy might help.
I think so.
Because it has the same dimensions.
Well, I think it was a good discussion.
That was fun, Matt.
Okay, thanks, Jeff, for sitting down with me for the podcast.
It's great. I hope people find it interesting. I don't know.
I'm sure they will.
All right. Well, thanks.
Okay, cool. Thanks again for listening to Numenta on Intelligence. This was a conversation on defining intelligence with Jeff Hawkins. I'm Community Manager Matt Taylor. Tune in next time.